Chapter 3, Applications Differentiation, and we spoke about this yesterday. If you want to print the notes, then by all means. If not, just pause the video and then restart it and I'll chat about these. Okay, extrema. Extrema is defined as a maximum or a minimum. An absolute, we'll refer to it as absolute. Some textbooks refer to it as a global extrema. So the minimum would be some value is less than or equal to every other value of the function. A maximum, you can find some y value that's bigger or equal to every other y value on the entire domain. If you think of the graph we looked at yesterday, the absolute maximum occurred because this y value was bigger than every other y value on the function. And then we said because the arrows pointed down, there was no absolute minimum. Okay, let's see here. Let f of x be the function x squared. For each specific domain, identify any absolute extrema. So when we're looking on the domain of the whole function, all real numbers, we would have no absolute max, but the absolute min would occur at 0. Okay, next, on the closed interval from 0 to 2. Alright, this isn't letting me change. 0 to 2. Absolute maximum would occur at 4. Absolute minimum would occur also at 0. Let me go back real quickly. When we talk about absolute maxes and mins, I need to make a note of this. We're referencing the y values of the function. Okay, so absolute maxes and mins, when you're asked to identify them, it's the y value of the function. Okay, now if we look, 0 is open and we're closed at 2. Alright, sorry, this keeps changing. Then we would have no absolute min because the y value doesn't exist at 0 because it's an open circle, and we would have an absolute max again at 4. Okay, now if we have both open at 0 and open at 2, no absolute extrema. Okay. So our first theorem, if f is continuous on the closed interval, and this is important, the interval has to be closed, then the function has both a maximum and a minimum on that interval. So just determine the extrema of 4x minus 1 given these specific domains. So when I look at C, according to the theorem, there definitely has to be an absolute max or min because it's on a closed interval. This is a line, so the domain of the function is all real numbers. Now for A and B, let's check out the graph. Y-intercept of -1, slope of +4. So on the domain of the function, all real numbers, there would be no extrema. Even on the closed interval, the open interval from -2 to 1, still no extrema would occur because there's not one particular y value bigger or smaller than every other y value of the function. When we close the interval from -2 to 1, though, f of -2, -9 would be our minimum. That occurs when x is -2. And then when we plug 1 into the function, 3 would be our maximum value. Okay, critical values in numbers. Take a minute and pause the slide for me. So the definition of a critical number, we have the function exists at some value c. x is equal to c is what we call a critical value of f if the derivative at c equals 0 or the derivative at c does not exist. So critical numbers are necessary to determine extrema. Alright, so absolute and relative maxes and mins are directly related to critical numbers. So to find a critical number or a critical value, again, it depends on the book or where we see the problem. They could be referred to as either. It's where the derivative equals 0 or the derivative doesn't exist. Now, if we think about graphically what the derivative equal to 0 means, then the function would have a horizontal tangent line at whatever value of c made the derivative 0. If the function didn't exist, the derivative didn't exist at c, the function could have a sharp turn, a cusp, or be an endpoint on the graph. And remember, here are 4 cases where the derivative does not exist. Alright, vertical tangent lines, discontinuities on the function, sharp turns and cusps, and then endpoints. If we talk about a discontinuity, okay, the derivative doesn't exist at a discontinuity on the domain of the function. So that's why we could look at it this case, but if it doesn't exist, if it's a discontinuity on the function, it would be a discontinuity on the graph of the derivative as well. Okay, so extrema occur at critical values or the endpoints of the function. So these 4 steps are the steps that we'll use to determine the extrema on a closed interval. So remember, the theorem says a max or min on a continuous function must occur on a closed interval. And that's this condition. Before we even start, the function has to be continuous on the open interval that's given. So the steps: find the critical values of the function, set the derivative equal to 0, find where the derivative doesn't exist, evaluate the function at these points found, evaluate the function at the endpoints, and then you just compare what the y values are. The highest y value would be the maximum, the lowest y value would be the minimum. So the directions for the next examples: determine the extrema if it exists of each function. Quadratic, domain is all real numbers. So start by finding the derivative using the power rule. So that's your first step. Your first step continued: find the critical numbers, find where the derivative equals 0, find where the derivative does not exist. And I exhaust both cases. So x equals 3/2. Domain of the derivative is all real numbers, so you won't have a derivative that doesn't exist, but I like you to write down both cases so that you're not forgetting this condition. Alright, second step, evaluate the function at the critical values. So take that critical value, plug it back into the original. So negative 9/4 plus 9/2 minus 5. So common denominator of 4, negative 9 plus 18 minus 5, or excuse me, minus 20. 9 minus 20, so that would be negative 11/4. Third step, evaluate the function at the endpoints of the interval. F of negative 2 would be negative 4 minus 6 minus 5, so that would be negative 15. F of 1, negative 1 plus 3 minus 5, so negative 3. Once you evaluate the function at the critical numbers and the endpoints, now you make your conclusion. So it's certainly clear to see that the minimum occurs at negative 15, or the minimum is negative 15, and the maximum value would be negative 11/4. And then you're finished. Okay, next function, derivative, again using the power rule. So that becomes 2 over the cube root of x minus 2. Set the derivative equal to 0. So where does this function equal 0? Alright, so I added 2 to both sides, and then I'm going to multiply by cube root of x and divide by 2 at the same time. So here's one critical number. X is in the denominator, so we do have a case where the derivative doesn't exist. Derivative doesn't exist at 0. 2 critical values, 2 endpoints. 1 and the endpoint, we would only have to substitute them in one time. Plug negative 1 in, you get 3 plus 2, a y value of 5. Plug in 0 to the original, you get 0. Plug 1 into the original, we get 3 minus 2, which is 1. Absolute minimum is 0. Absolute maximum is 5. Okay, our next function, to find the derivative, we need the quotient rule. Bottom function times the derivative of the top minus top times the derivative of the bottom, all over bottom squared. Distributing the 2, multiplying the 2 x's. So negative 2x squared plus 2. So critical numbers, the derivative of a rational function equals 0 when the numerator is 0. So subtracting 2 and dividing by negative 2, x squared is 1. So we get 2 critical numbers from that case. A rational expression, does not exist when the denominator equals 0. Attempting to solve this function, we would get x squared equals negative 1. So we get no critical values from that condition. So plugging in the 2 critical numbers and the 2 endpoints, f of negative 2 would be negative 4 all over 5. F of negative 1, negative 2 over 2. F of 1 would be 2 over 2. And then f of 2 would give us 4 over 5. So absolute minimum is negative 1. Absolute maximum is positive 1. Okay, so the next 2 examples I have are trig, but for the interest of time, I'd like you to try these on your own. So for homework, attempt to, same directions, determine the intervals, determine the extrema of the function, if it exists. Alright, and the steps, okay, critical values, critical numbers, evaluate the function at the critical numbers, evaluate the function at the endpoints, and then draw your conclusion. Okay, I'll see you on Monday.